Hi, welcome to a new lecture on ways to make gradient descent better for machine learning. This is part of a 4-lecture module where in the last 2 lectures we covered stochastic gradient descent and momentum based gradient descent. Today we'll be looking at RMSprop or root mean square propagation, which is also another method to make the vanilla gradient descent or the batch gradient descent much better. This module is part of the course Foundations for Machine Learning. So even if you don't know what is gradient descent, don't worry, I'll be covering that in the beginning of the lecture. So I'll be providing you a recap of what exactly is gradient descent. So this is the third method that we'll be discussing, RMSprop or root mean square propagation. So first let's do a brief recap of gradient descent. So gradient descent is nothing but a way to minimize loss. The loss is nothing but the difference between, it's an estimate of how far off you are from the actual data, how far off your model's prediction is from the actual data. The loss is denoted by loss function or cost function j, so j of theta. So here theta is the model parameters. If your model is a linear regression, theta is the slope and intercept. And what you are essentially trying to do is find the slope and intercept or find the theta which minimizes your loss. So how do you find this theta which minimizes your loss? You move along a landscape, which is the j of theta function, such that you are reaching a global minimum, ideally a global minimum of j of theta function. And so here this is the equation which basically performs one step of gradient descent. So the new value of theta equal to old value of theta minus learning rate times gradient of the loss function itself. So the learning rate is something that tells okay, you calculate the gradient, but now by what extent do you want to take a jump from the previous value of theta to a new value of theta? And why is it called gradient descent? Because you are going against the direction of the gradient, because you are not going to go to a direction where the loss is increasing. You want to decrease the loss, so you move against the gradient of the loss function. So that is why there is a negative sign and theta is the parameter. So there are a few simple to understand steps. Step 1 is start with a random value of theta. So you assume that the slope of the linear regression line is something, the intercept is something. I usually start with 0, 0. Then you calculate the gradient of the loss function when the slope equal to 0 and intercept equal to 0. There are other models also. I am talking about linear regression because it's the simplest model. Then after you calculate the gradient, you update the parameter based on this above equation. And then you repeat the steps 2 and 3 until convergence or until a predefined number of steps. So this is basically the vanilla gradient descent or batch gradient descent. The reason why it's called batch gradient descent is because here the j, it is equal to mean squared error in the context of linear regression. So this will be 1 by n times sigma y I predicted minus y actual the whole square. So this is the mean squared error squared, and we are taking the mean. So here actually we are taking the mean by using every single data point. So I can run from 1 to n, where n can be 1 million, n can be 100, n can be 100 million, whatever is the number of data points. So the problem with this vanilla gradient descent is that it's computationally not efficient for large data sets. There can be, if you have a noisy loss surface, meaning if the function j is not a smooth function with respect to theta, then there will be convergence issues. So when I say not a smooth function, I mean something like this is a very smooth function. It's not very, the j is not very noisy, but if the number of parameters for theta is not 1, if there are many parameters theta like slope, intercept, and there itself slope with respect to dimension x1, dimension x2, etc. There can be like directions along which the j function has local minimas and global minimas, etc. So j function can look like a weird shaped graph also. And in these examples, the vanilla gradient descent will struggle to arrive at a proper something close to a global minima. So in this lecture today, we'll be looking at a technique called root mean square propagation or RMSprop. So RMSprop is, I wanted to teach this because so that you can understand 2 different ways in which you can deal with step sizes. So in the previous lecture in in momentum gradient descent, we were using a constant value of learning rate, and then we were changing the step size by using a term called velocity. So the velocity term replaced the term which was the gradient itself. So basically, if our equation was theta is getting replaced by theta minus eta times gradient of j with respect to theta. Instead of this, in momentum we had theta minus eta times vt, and vt was the velocity at time step t, which was vt minus 1 times beta, plus gradient, which is gradient of theta, gradient of j with respect to theta times 1 minus beta. So you are taking a fraction or a small fraction of gradient plus a big fraction of previous velocity as the current velocity, and you are using this. Now here in RMSprop we will be doing something else. So the problem with vanilla gradient descent is that learning rate, and this is also the problem with momentum based gradient descent or even stochastic gradient descent, the learning rate is the same. This eta learning rate parameter is the same. We are not changing this. This can be an issue because see, if there are oscillations, for example, if j is this, theta is this, and if your j as a function of theta looks like this, there can be oscillations like this, making the convergence very, very slow. Sometimes there can also be issues where, because the initial learning rate itself is too big that you picked, then there can be divergence. Instead of converging, the slope, I mean the value of the loss function can diverge to big numbers like 10 raised to 50, 10 raised to 35, big numbers. So an adaptive learning rate is very much useful if you can change the learning rate according to what the situation demands. And that is one philosophy behind the root mean square propagation. And sometimes some parameters may have much larger gradient than others. And by this, what I mean is it cannot be displayed on a one-dimensional graph. But let's say you have parameter x1 and x2, and let's say this is j. Now j is a function of two variables. So this will be like a parabola, but I mean parabola, if parabolic is the shape of the loss function, then this will be like a parabola, but it has both dimensions x and y. I mean it has both x1 and x2 parameters, so that it's like a 3D surface. Now in this case, it can so happen that the j of, let's say, x1 comma x2, it is something like 1 times x1 square plus 100 x2 square. So from here, if you calculate the gradient, dou j by dou x1 equal to 2x1, but dou j by dou x2 equal to 200 x2. So for the same value of x1 and x2, the j has a much rapid change along the axis of x2 than along the axis of x1. And in these cases also, there will be issues when we are using vanilla gradient descent, because this guy will completely increase the value of the total net gradient, because dou j by dou x1 is a huge value. But we'll see how RMSprop can fix this by normalizing the gradient using their magnitude history, meaning in the previous time step, if the gradient was very big, even in the current time step, if gradient becomes too small, we will see how RMSprop can fix the value by which parameter is updated by having an adaptive learning rate. So RMSprop can obviously, I mean, one of the reasons why this was proposed is because it can mitigate the oscillations that can happen when there is steep loss function or big learning rate. And in flatter regions, you can have much better convergence, because in flatter region, typically the problem is if this is j of theta and if this is theta, and let's say the graph shape is something like this, this is a flat region. And if the learning rate was not adaptive, the problem is that at a fixed learning rate, when the gradient becomes very small, then theta nu equal to theta minus eta times gradient of j, right? Now, if this becomes a very small number, this whole term will become very small. So in this flat region, the rate at which theta will change, you will move like an ant. You will be moving very slowly until you find a region where there is a significant gradient. But if we had an option to have adaptive learning rate, even if gradient of the loss function is very small, you could increase the learning rate to take bigger steps. So instead of moving in small steps, you could take bigger jumps, right? So this is something that RMSprop can do. So let's discuss mathematically how RMSprop works and how to implement that. So the first step, as usual, is to compute the gradient of loss function with respect to theta. So theta j, gradient of j with respect to theta, and this is the vanilla gradient, normal gradient. Now after this, we maintain a moving average of the squared gradients. Now what is a squared gradient? This is a squared gradient. The gradient, whatever we calculated before, we are squaring it so that the sign does not matter. Whether the gradient is positive or negative, it doesn't matter. We are just squaring it. So squared gradient at time step t. Now what is the moving average of the squared gradient? The moving average of the squared gradient at time step t is equal to the moving average of the squared gradient at time step t minus 1, and we are taking 90% of that because beta is 0.9 typically. It can be 0.99 also depending on the problem statement, but we will say that the moving average of the squared gradient in time step t equal to 90% of the moving average of squared gradient at time step t minus 1 plus 10% of the squared gradient at time step t. So this gt square is gradient at time step t squared, and 1 minus beta will be 0.1 because beta is 0.9. So we are taking 10% of the current gradient, the square of current gradient, and 90% of whatever was the moving average of the gradient in the previous step. Now you might be wondering, okay, what is this moving average? You'll be able to visualize that only if you are starting to think from the time step t equal to 1, the very first step. But we'll come to that while implementing. Now for scaling the gradient, what are we going to do? We are changing the learning rate. So here, instead of in the vanilla gradient descent, we had theta in time step t plus 1 equal to, or rather theta at time step t equal to theta at time step t minus 1 minus eta times gt, right? Gradient at time step t. This is vanilla gradient descent or batch gradient descent, BGD. This was the formula, but in RMSprop we use another formula, which is theta at time step t equal to theta at time step t minus 1 minus effective learning rate, or maybe a better notation is learning rate at time step t times gradient at t. Now you might be wondering, what is this learning rate at time step t? Learning rate at time step t is whatever was the constant learning rate we defined divided by square root of the mean of the gradient. So square root of moving average of the gradient till that time step. Actually I can put the t outside, but anyways does not matter, plus epsilon times there is no times, we are just talking about effective or the value of eta at a given time step. So now here epsilon is a very small number, like 10 to the power of minus 8, so that in the first time step when gt is 0, you are not dividing by 0, but rather you are dividing by 10 to the minus 8, 10 to the power of minus 8. So here what this is saying is, imagine that your gradient was completely 0. For example, let's say your function looked like this. So and this is j of theta versus theta, right? And imagine that you start with a random value of theta, right? So you start, let's say you are starting from here. Here the slope is very, very small, meaning the moving average of the square of the gradient is a very small number. So if eta was let's say 0.1, then gt, the gradient is a very small number here. So let's say gradient is 10 to the power of minus 8. Then the square of moving average will be something close to 10 to the power of minus 16 at this region after 1 or 2 time steps. But then what you do is effective eta. So what happens is, in vanilla gradient descent, theta at time t equal to theta at time t minus 1, which is whatever this initial theta is, minus, let's say learning rate is 0.1 times gradient. Gradient is very, very small here. Let's say it is 10 to the power of minus 8. You are effectively not changing theta. You are changing theta by 10 raised to minus 9. You will wait until the end of universe to get a meaningful change in theta. But in the RMSprop, you are doing theta t equal to theta t minus 1 minus 0.1 divided by square root of, let's say, 10 to the minus 16 plus 10 to the power of minus 8 times 10 to the power of minus 8. Because eta divided by square root of that effective gradient, which we assume to be close to 10 to the minus 16 plus epsilon. Now this is how much? This is theta 10 to the minus theta at time minus t minus 1 minus 0.1 divided by, this is square root of 10 to the minus 16 is 10 to the minus 8. So this will be 2 times 10 to the minus 8 times 10 to the minus 8. So power of minus 8. So this is theta t minus 1 minus 0. This cancels. So it will be 0.1 divided by 2, which is 0.05. Now see, you are, instead of now changing theta by 10 to the power of minus 9, you are changing by a much bigger number, so that you can take a bigger step here. Instead of moving by 10 to the power of minus 9, which is literally very, very infinitesimally close to the original point, you are taking a bigger step so that you can traverse this region where the loss function is almost flat at a much more faster rate. And this can bring a much more faster and more efficient convergence. So this is the conceptual idea behind RMSprop. So you are having an effective learning rate in this case. You can think of this in two ways. Either you can think that the learning rate is constant and you are kind of adapting the the gradient itself. So you can say that learning rate remains as eta, but the gradient will be gt divided by square root of the square of moving average. Moving average square, moving average of squared gradient, plus epsilon. You can say that this is the effective g gradient and eta remains the same, or you can say gradient remains the same, but you are adaptive, you are having a adaptive learning rate. Either way you can visualize this. Now here what we are doing essentially is that we are normalizing the value of the gradient. Okay, one more example that I want to show you is the opposite case of this. So here, let me delete whatever I have written. Now look at the case. So we discussed the case where gradient is very small. What about this? What about the case where gradient is huge, like something like this? So if gradient is huge, and let's say this is j of theta and this is theta. If gradient is very, very big, what happens is, if you start from here, you will change the value of theta by a lot. So here theta t equal to theta t minus 1 minus eta times gradient gt. Gt is the gradient, right? So here the gradient, let's say it is a very big number, like maybe 10 raised to 3, something like that. Then actually minus 10 raised to 3, because gradient is negative. So then theta t in vanilla gradient descent will be theta t minus 1 minus, let's say learning rate is 0.1 times minus 10 to the power of 3, and this will be equal to theta t minus 1 minus plus 10 to the power of 2, because 0.1 times 10 to the 3 is 10 raised to minus 1 times 10 raised to 3, which is 10 raised to 2. So you are saying now theta is changing by 100. So here if theta is 1 or whatever number this is, you are now jumping all the way till 101. So you are jumping into an even worse situation, because you are going from here, and now at 101 maybe the slope is somewhere huge over here. Then you will jump back here and then you will diverge. So your algorithm is dead, your gradient descent is dead basically. But instead, if you follow the root mean square propagation, what you need to do is theta t equal to theta t minus 1 minus eta divided by square root of root mean square. So e of gt square, e of g square at time step t plus epsilon times gt. Now if you are in the time step 1 or time step 2 or something like that, the moving average will be, say, very close to the current value of gt. So let's say this is equal to, so which means you can say that this is approximately equal to the square of the gradient itself. So let's say 10 raised to 6, something close to that. And then this will be theta t minus 1 minus 0.1 divided by square root of 10 raised to 6 plus 10 to the power of minus 8 epsilon, a small value, times gradient itself. Gradient was 10 to the power minus 10 to the power of 3, right? And then this becomes equal to theta t minus 1 minus 0.1 divided by 10 raised to 3 multiplied by minus of 10 to the power of 3. So now this both can cancel, and this will become theta t minus 1 plus plus 0.1. So now you are moving on by a reasonable distance. So you are moving from 1 to 1.1, and then you will go from here to here instead of going. So this is what happens to the gradient descent. Instead of jumping from here to here and then here and then here, right? So what essentially we are doing is we are scaling the gradient down if the value of the gradient is so big. We are scaling the gradient up if the value of gradient was too small. And how are we doing this? Effectively by having a learning rate. So you can visualize it to be scaling the gradient or scaling the learning rate. Either way, it's fine. But I hope you get the idea here. So this is a very efficient way to perform gradient descent based on the value of the gradient at a time step t. All right. Now, so that is what we are saying. Tracking the magnitude by averaging the squared gradient, root mean square propagation, adjust the learning rate for each parameter based on its recent behavior. Then dampening the oscillation, this we will see when we are implementing. Why do you call it as dampening the oscillation? Where exactly is the oscillation coming? This you will see when we plot loss as a function of epochs, because in momentum gradient descent the loss goes something like this. In root mean square propagation you will see what do we mean by dampening the oscillation. So this we will see soon. Now just one more thing to please understand: root mean square propagation does not incorporate momentum. The reason why I am mentioning this is in the next lecture we'll be talking about Adam optimizer. In Adam, actually there is both momentum as well as adaptive learning rate. In momentum there was no adaptive learning rate was constant, but the gradient was kind of modified based on the velocity or based on the momentum. In root mean square propagation the gradient remained the same, but we changed the learning rate based on the past value of gradients, past or the history of gradients. So momentum is not there, but in the next one, Adam, you will see how you are changing, you are incorporating both the momentum as well as adaptive learning rate to get the best of both worlds. So that's I just wanted you to remember that RMSprop does not incorporate momentum. Now let's implement the RMSprop in Python, and as usual I have already tried and tested the code. I have written it and tested the code. It works really well, but I have chunked it or split it into different modules. So I will walk you through the code first, the different blocks of code, so that you can it makes sense to you, and after that we can implement the code in Google Colab. So let's get into coding. As always, we import the libraries first. So NumPy for arrays, Matplotlib for plotting graphs. Then, so I'll move a bit faster to the portions where I'm sure you are very comfortable. Second is defining the quadratic loss function. So here j of theta equal to j of x comma y equal to x square plus 10y square, right? So this is the loss function. It's not like x is the input and y is the output. It is a convention that we usually use, right? So please don't get confused when we use this kind of a notation for the loss function. I mean, for theta, we are using theta. One of the parameters is x and other parameter is y. So it's like a quadratic loss function. Then the gradient will be dou by dou x is 2x, and dou j by dou y will be 20y. So that is what we have here, quadratic loss function. So I hope these parts are fairly clear. We have already covered this in detail in the past lecture, which is why I'm not spending too much time on the loss function itself. It's fairly easy. If it's not too clear, just pause the video and just think about the shape of J. It will look like a parabola. So x, y, so this can be x, this can be y, this is j. It will look like a parabola, but it will have both x and y dimensions along the independent axis. And from top, it will look like an ellipse. The iso equal value contours, whatever it is called in iso terms, it will look like ellipses. So in this case, it will look like an ellipse elongated along y-axis. Now, vanilla gradient descent, let's implement as a function. So we will start from a particular starting point on the loss contour. So starting point is random. Then we will store the path so that we can plot the path. We can see where the vanilla gradient descent is taking these xy points after each iteration. And we will also store the losses in a variable continuously, iteration after iteration. So the losses are appended to this variable after each iteration. So that finally we can plot the losses for all the time steps, all the iterations that we took. And we have a function called grad function. Grad function is nothing but we are passing this quadratic gradient, which is the gradient function of this quadratic loss function. So we are passing it here wherever we are calling the gradient descent. We are passing this quadratic gradient function into this variable. So basically, when you call grad function with some x comma y, it will return 2x for dx and 20y for dy. So it will be an array consisting of two variables, of two values. Now, the first value of that is dou loss by dou x, and second value, which is grad of 1, will be dou loss by dou y. So now you will be changing x minus equal to, meaning x equal to x minus learning rate times gradient in the x direction, y equal to y minus learning rate times gradient in the y direction. The previous one was the gradient in the x direction. Then we will append to the path variable the current value of x and y, so that later we can plot and see how the values of x and y are changing along the contours of where the loss function is constant. And then we return the array which stores the path and the array which stores all the losses for all iterations at the end of the function. Then we have another function for implementing root mean square propagation. Root mean square propagation is fairly easy as well. So we have a starting point. Then we have the average of the square of gradient. Initially, we are starting with 0 because even in momentum, if you remember, we started with 0 velocity in the first time step. Exactly, we'll be doing the same thing here. And the initial path will be in the path variable. We will be storing the initial path x and y points. So x and y, please remember, they are not input and output pairs. They are the two parameters which define the loss function j. Okay. And then we are storing the quadratic loss function, the value of the quadratic loss function in the losses variable. So losses we will keep on appending after every iteration. Path also we will keep on appending after every iteration, so that finally we can plot path and losses as two separate graphs. And now, how are we changing the x and y values? It is exactly the same. So learning rate is same as before. Gradient is also same as before, but the learning rate we are modifying by dividing by. So it's like learning rate divided by np dot square root of the moving average of the squared gradient 0. So this is along the x direction plus epsilon, and epsilon is a very small value, like 10 to the minus 8, 10 to the power of minus 8. So x equal to x minus learning rate divided by square root of the moving average of square of gradient, square root of that plus epsilon, and y equal to y minus learning rate divided by this guy times gradient of the loss function along the y direction. We have already discussed the formula in detail. Here we are calculating the gradient, and here we are calculating the moving average for time step t based on moving average from previous time step and gradient of the current time step and square of gradient of the current time step. So square of gradient of that current time step is grad square, and 1 minus beta means the moving average of the square of gradient in the current step is 90% of the moving average of the moving average from the previous step plus 10% of the square of gradient from the current step. So, and why do I say 90 and 10? Because I assume that the beta value is 0.9. If beta is 0.99, then where is the beta? Yeah, beta is 0.9, that what we are using. So 90% of the previous moving average plus 10% of the current gradient. Now, so that is the RMSprop function. Then we have two functions to visualize paths. I'm not going into the details of this function. It's fairly easy. You can pause the video and go through this. I don't want to make this lecture into a data visualization lecture, but we are visualizing the paths first in this function and we are visualizing the losses. You will see when we plot this exactly what the losses and paths look like. Losses look something like this. Loss as a function of epoch. And it will look something like this typically, right? And then we are defining the parameters. So in the normal gradient descent, learning rate is 0.1. In the RMSprop also, learning rate we define to be 0.1. Beta is the decay rate, 0.9. Epsilon, the small value that we are adding to the square root of the square root of the moving average in the denominator is 10 to the power of minus 8. Number of epochs can be 100, 50, whatever we think is good. Starting point of x comma y. So in j of x comma y, we are starting with some random value of x comma y. It will be 1.5 comma 1.5. Then we run the normal gradient descent with these input parameters, and we run root mean square propagation optimizer or that gradient descent also with same set of parameters, but in addition there will be beta and epsilon. And then we store the path and the losses, for both of these, so that we can plot the path and compare how it looks for the normal vanilla gradient descent and RMSprop, and also plot the losses and compare that for these two different types of gradient descents. So this is the plotting the results part. So now it's a good time for us to open Google Colab and implement this code and play with the code and see what the output looks like and how we can compare the normal vanilla gradient descent and RMSprop. So feel free to again use Jupyter Notebook or whatever platform you are comfortable with. I'll be coding in Google Colab. So here is the empty Colab notebook and we can start putting the code. So first importing libraries. Just run that, defining the quadratic loss function x square plus 10y square, gradient dou by dou x equal to 2x and dou by dou y equal to 20y. Then vanilla gradient descent code, that this is just a function, so obviously there is not going to be any output until you call the function. Then the code for root mean square propagation, again just the function, no calling is involved. And the function for visualizing the path that the parameters take along the contour of the loss for both gradient descents, both types of gradient descents, and then finally visualizing the loss. Again, this is just a function, we are not calling it yet. Now we'll be defining the parameter, that is this part of the code. I'm just copy pasting it fast, assuming that you have already understood the different sections of the code, so there is no need to make the video long by going too slow. So here we are defining the different parameters. Again, function calling is not involved. Here is where we are calling the function for the first time. So we'll call gradient descent function as well as the RMSprop function. And when we run this, no output is going to be displayed because path will be stored here in both cases and losses will be stored in this and this variable in both cases, and we have to plot them to get any kind of visual output. So let's plot the paths first. I'll plot the losses later. So let's plot the path to see how the gradient descent looks in both of these cases. So you can see that in case of root mean square propagation, it's very different from momentum, by the way. In momentum, it was going as if a ball was rolling. In this case, in root mean square propagation, it's not looking like a ball rolling. And what is this graph, by the way? This is a graph of x versus y. X and y are parameters of the loss function, and we are looking at the contours. These ellipses are contours where the loss function has a constant value, right? So, and in normal gradient descent, you are moving along the direction of the steepest descent in the normal gradient descent, which is the vanilla gradient descent, and you can see that there is oscillation here. So the values of x and y is oscillating from, so it goes from 1.5 to the x value goes from, or rather y value goes from plus 1.5, here it becomes minus 1.5, here it again becomes plus 1.5, minus 1.5. So the value of y is oscillating, whereas in RMSprop the value of x comma y is slowly it starts from the 1.5 comma 1.5. So the starting point for both vanilla gradient descent and RMSprop was 1.5 comma 1.5. So you can see this green dot. So the green is the starting point, and in the green dot the x value is 1.5 and y value is also 1.5, and green dot is overlapping for both cases, gradient descent and RMSprop, because starting values are the same. But the ending values, you can see that the final red dot associated with RMSprop is somewhere here, and we know that if the loss function is x square plus 10y square, the minimum value of the function occurs when x equal to 0, y equal to 0. So indeed x has become equal to 0 and y has become equal to 0 in RMSprop. On the other hand, in gradient descent, you can see that there is a red dot here, x equal to 0 and y equal to 1.5 in that case, and the value has not been optimized. The loss value in this case will be x square plus 10y square. Since x equal to 0, that term is cancelled. 10y square will be 10 times 1.5 raised to 2, which will be 10 times 2.25, which will be 22.5. So the final value of loss ideally should be 22.5, and we'll see that when we plot the loss function. So let's plot, not the loss function, the value of loss. So let's plot the loss, and we should see that so here you can see that the loss in case of gradient descent is 22.5 in the case in the asymptotic case, and you can see that the oscillations are not there, unlike in the case of momentum. In momentum there were oscillations in the value of the loss was decreasing, then increasing, decreasing, increasing, and finally settling down. In stochastic gradient descent it was very, very high. Now to even highlight this point, so let's increase the learning rate from 0.1 to 0.2. So if learning rate is 0.2, of course there is a chance for the normal vanilla gradient descent to diverge, and indeed it has diverged. You see the ellipses have vanished. X value and y value, you can't even see the ellipse because it's all compressed into one small region here, because see the y value is going from 0 to 10 raised to 47. X value is just going from 0 to 2. So and that's because the ending value, the y coordinate of the end of the last point at the end of the iteration, gradient descent has reached to a y coordinate value of something like 8 times 10 to the power of 47, a huge, absurdly huge number. And you will see the same thing with loss. See, the loss is diverging. Loss is 10 raised to 96 for the normal gradient descent, whereas RMSprop loss is very close to 0. And what happens if the learning rate is small, 0.01? In this case, of course, the vanilla gradient descent is going to be very smooth, because it will directly go to the optimum. So the vanilla gradient descent is getting closer and closer to optimum. RMSprop is directly going there. So let's do one thing. Let's increase the number of epochs to 150. Again run, so that we can see that in both cases there is convergence. Okay, maybe so at 150 the loss, so normal gradient descent already reached a lower value of loss, so at maybe like 40-60 iteration, but RMSprop is slower. But if we have around 200 iterations, the final value of the x comma y should be close to 0, 0 for both of these cases. You can see that here. So and now the losses for both cases are very close to each other. So the conclusion is that if the data points are, if the not the data points, if the learning rate is very small with sufficient number of iterations, of course you can reach a very good convergence with the gradient descent. But the problem is execution will be slow. If the learning rate is kind of optimum, the gradient descent, you can achieve a faster or better convergence using RMSprop. Okay, when I say optimum, I mean if the learning rate is intermediate, Maybe it is likely that in the normal gradient descent there can be oscillations like how we saw with learning rate equal to 0.1, but RMSprop there was no oscillations. If the learning rate is high, the gradient descent can diverge and go to absurdly huge values of losses, whereas RMSprop will not do that, because there we are taking the moving average of the square of the gradient. So as we discussed, when gradient is small, it will be normalized to a higher value so that the parameters can be updated appropriately. If the gradient is high, it will be scaled down using the adaptive learning rate, so that the changes, you won't be changing the value of the theta by an absurdly huge number. We discussed that mathematically during the first part of today's lecture. So I hope this brings a lot of clarity to you with respect to how the RMSprop works. There is a lot of similarity between RMSprop and the way we implemented momentum, and you will see even more similarity in the next lecture when we implement Adam optimizer, which is the most famous optimizer. So the conclusion is that if you use vanilla gradient descent, it's very difficult to obtain very smooth convergence with a somewhat high learning rate. You have to reduce the learning rate and you have to increase the number of iterations, which of course increases the computational cost. You can overcome, we saw that you can overcome that using stochastic gradient descent to some extent. Even better way, you can overcome that using momentum. And in today's lecture, we saw you can also overcome that. You can get better results for the same computation cost or similar computation cost with RMSprop. So that brings us to the end of this lecture, and as usual, let me take a moment to appreciate you for reaching all the way till here in this course, and thank you so much. We'll meet again in the next lecture. Take care until then. Bye.